Welcome to episode 11 of our little series on Vertex Operator Algebras. It's Saturday, bonus episode. Today we will construct the induced modules of a Lie algebra, and our main piece of technology is the universal enveloping algebra. Lie algebras are non-associative, so getting the canonical inclusion used by the universal mapping property of the appropriate induced module is tricky. FLM invokes the Poincare-Birkhoff-Witt theorem, which provides both the canonical inclusion map and a basis for the universal enveloping algebra in terms of the Lie algebra. We make no attempt to prove this theorem either, but we'll drop the appropriate references in the lecture notes. For example, see the text by Humphreys on Lie algebras and representations. Let's get started. Consider the tensor algebra associated to a Lie algebra G. The tensor algebra has a natural associative structure, courtesy of the tensor product, and as we saw in section 2, commutators can help make that compatible with a Lie algebra. While the tensor algebra certainly has an identity, the unit vector in the 0th tensor power, there's no canonical way to identify a corresponding element in G. As discussed last time, the tensor algebra has plenty of ideals with which to quotient. Today we'll look for a new one that again represents a Lie bracket with a commutator. Specifically, we're going to be looking at the ideal generated by elements of the form x times y minus y times x, minus the Lie bracket of x with y. As usual with these sorts of ideas, the intention is to effectively equate these objects inside the tensor algebra. This construction, the quotient which extends the Lie bracket to commutators in the tensor algebra, is called the universal enveloping algebra of G, often denoted U of G. One quick observation we will use in later episodes. If the Lie algebra is abelian, the universal enveloping algebra reduces to the symmetric algebra, which inherits the universal property from associative algebras. For a general Lie algebra, the quotient taking in U of G obscures the would-be canonical inclusion map, I into U of G, and this is where FLM invokes the Poincare-Birkhoff-Witt theorem, which gives two results. First, it says that the canonical map from G into U of G is injective. It also provides a basis for U of G, which can be modeled by ordered products of basis elements of G. So all is pretty much as you'd expect it to be, but fair warning, the construction is non-trivial. The induced module. So given a subalgebra H of a Lie algebra G and an H module V, we can induce a G module as the balance product of U of G and V, with respect to the algebra multiplication from U of H. Evidently, this construction preserves a grading, assuming G, H, and V are all Fraktur A graded. Let's dig a little deeper and derive a result that we'll use later when discussing Heisenberg algebras. Suppose G is decomposable, in the sense that G is the direct sum of two Lie algebras F and H. A consequence of the Poincare-Birkhoff-Witt theorem is that U of G is isomorphic to the direct product of U of F and U of H. See episode 7 for a refresh on direct products of Lie algebras. As an exercise, show that, for this decomposable scenario, that U of G module induced by V is isomorphic to the simple tensor product of U of F and V. To do this, you might consider elements of the form AB times V, where A is an F and B is an H. Let's do a quick roll call on the induced modules that we've discussed so far. For associative algebras, to expand the module to include the action of the full algebra, we need only take the tensor product of A with V, taking the appropriate quotient, of course, the middle linear product with subalgebra. For groups, we must first embed the groups in a group algebra. Group algebras are an expansion of the group structure to include a field action. Group algebras afford the requisite associative algebra structure to create the induced module. For Lie algebras, we must first embed into the universal enveloping algebra, which, being a quotient of an associative tensor algebra, is considerably more complicated, a more expansive structure. But that said, U of G is universal in the sense that it contains every other representation of G. So hey, that's our show, and congratulations on making it this far. Next week, we're going to begin to dig into the details of affine Lie algebras, what physicists might call Kasmuni algebras, and this will bring us to the front door of Vertex Operator Algebras. See you next time.